Like I said, we know most of this stuff already. It's pretty simple since it's the first two parts. But yeah, the first module is just intro to data structures. So we're going to, explain how data structures are used, define the five basic operations, and build an array to perform basic functions. I hardly doubt none of us don't know this stuff, but yeah, it's like a container that stores data in a specific organized layout. You can see it by the table. You can see like the bed's the data point, and the furniture is the data structure part of that. And it's also organized in some way. Okay, so before you can access, add to, or search in a data structure, we have to choose the type of data we want to use. Data can be structured in lots of different ways. Each allows us to use to do things with the data more or less efficiently. No one data structure is equally efficient for all actions, and some data structures don't support certain actions at all. That's why it's important to structure your data well from the get-go. For example, this structure is helpful if we're moving, but not quite so useful if we're trying to figure out stuff in the apartment. So obviously the most simple type of data structure is an array. I think we've gotten pretty familiar with that. It's a collection of items that can be accessed individually via an index that lists the position of the items in the array. Some of the characteristics of arrays. They're indexed, like I just said. In most programming languages, it starts at 0. Depending on the language, can be either fixed size or changeable size. I don't think we've had any encounters with fixed size yet. I'm not sure on that though. And typically it's one data type, so integer, strings, booleans, etc. Here's the 5 basic operations. Create a new array. You can create a new array of length, return a size, return a specific value of an index, or set the value of an index. So those basic operations. They're also excellent choice for storing data when you know the exact size of the data set. So that would be like, yeah, if you're like a meteorologist or something, you can get the average temperature for each day of the past week, or because we're computer scientists, you can format the data array like that. Yeah, and saying you'd use the loop to do that. Limitations. Let's see. Yeah, it's just saying that you can't answer all the questions you might ask about the weather data. Like, if there's 2 days that have the same average temperature, which temperature appears the most? Obviously have to write additional code to figure that out. We could just use a different data structure. An alternate structure may allow us to store the data points, for in this example, the temperatures, in a way that answers our questions without having to write any extra code. And these are just all the data structures that are covered in this entire module, which are arrays, linked lists, which is we're about to go over, stacks, queues, hash tables, sets, binaries, trees, ABL trees, and graphs. Okay, so this is the linked list section. We'll define a linked list, explain how a node stores data, define whether to use a linked list or an array for a given scenario, and build a singly linked list. So linked list is a foundational data structure used by many complex data structures. Key component is a node. Other advanced data structures use nodes too, but linked list specifically, a node is a unit containing 2 things at the same time. The data property is the stored value, and the next property, or the pointer, points to the next item in the list. So in this case, the only exception would be the last node, which they call the null next node, or the tail. So So pros and cons of linked list. They take up more space than arrays because you have to store both the pointers and the data. It can take more time to access a linked list because the data set isn't read as one continuous chunk. And you can't access a particular node in a linked list without starting from the top and moving sequentially until you find it. So that's unlike an array because, you know, you can quickly find an array, a value based in an array because, yeah, it's linear. So here's the efficiency in big O notation based on arrays versus linked lists. So yeah, let's look over that for a second. Okay, visualization. When you're building a linked list, the data and pointer properties of each node change as you build it out. So here's a little sketch of what that looks like. Any linked list starts with the head property that references the first node. When we start catching the list is empty. So we'll set the head pointer as null because we don't have any other nodes or data values. The default place to add more nodes to linked list is at the end of the list. The first node must be set as the head. So we'll add a next pointer and the new node with data. But by default, the new node won't need a pointer because it's the last node in the list. So the pointer will have a null value for now. For all future nodes that we add, we can add the last node by looking for the node with null as its next value. And once we find it, we can change its next property to now point to the new node we're inserting into the list. So traversing a linked list, in order to search for a specific value, access a specific point, or insert a value in a linked list, we first need to write the code that traverses that list. So that's what the code looks like for that. In our example, the walker variable contains the idea that the variable walks through the list one node at a time. The next property points the walker variable to the next node in the list and continues to do so until we reach a node that doesn't have a next property. That's how we make the code traverse the list. If we want to search for a specific value or access a specific point in the list, we write a conditional inside of the loop to read each node as we go. So the importance of pointers. Manipulating a linked list comes down to changing the pointer value of various nodes. So if you're inserting or removing nodes in a list, it's critical to ensure that your next pointers never lose reference. Inserting a new node at the end of the list is pretty straightforward, but placing one at the front or the middle of a list can get pretty messy. If a next pointer is broken, the rest of the list will be impossible to reference. So single versus double linked lists. So far, we've been trying to make single linked list. They go in one direction ahead to the next node in the list. But a double linked list, the first node points one direction, but then allows us to traverse the list backwards too. We can move quickly from the last node and then back from the last to the first node. To understand how this works, let's recall the properties of a node in a linked list. Both singly linked and doubly linked lists share these properties, the data and the next property. But doubly linked list has a previous property to the previous item in the list. The upside of doubly linked list is it gives you more mobility than a singly linked list. The downside is that it makes adding and removing values much more complicated because there are now two pointers, next and previous, that must be managed as you do so. So there's a little diagram that kind of visualizes that.
So you could do walker.previous and it goes backwards.
Essentially, yeah. I don't fully really understand that. That's one of the things I didn't really know about when I was looking at this. I'm pretty sure you can, though, yeah.
Yeah, okay.
So uses of linked list. It's common for a linked list to be used by itself. More often, it's the basis for other data structures, particularly stacks and queues, which I think we go over tomorrow, right? So if you think of like a playlist of your favorite music, that's a doubly linked list because each song points to the previous and the next songs. Another example would be like an image viewer, like just like your gallery on your phone, really, I guess. Some file systems are also built as linked lists based on the way they store data. Files are often stored in chunks, but if they get too large, they might not fit into the original chunks. Those chunks are just nodes of data with links to the next section of a file that's stored in another node. So this is maybe how like linked lists might appear in interviews. Apparently they're a common topic. And there's a link to some example questions right there. But the main ways they would be asked would probably how would you implement one? Adding and removing nodes from a linked list, which is what we just did basically in that question, or traversing a linked list. These concepts will appear in whiteboarding problems. So checking out this link right there on Geeks for Geeks, actually pretty good for understanding the more like finite details of this type of thing. It says right, you won't even know how to visualize the code of a linked list, but I mean, it's probably still good to know that. And here's the little tool you can use to visualize it. Yeah, that's it for those two.
Cool.
Any questions?
So I wonder what adding a node looks like. So removing, you just make walker equal walker.next next, right?
Mm-hmm.
To add, I wonder what it looks like.
It would really depend, like, where you're doing it.
Yeah. Where was that? There was I had a slide about that actually.
So appending is if you want to add it at the tail, and then prepend is if you want to add it in the beginning.
And append. Okay.
Yeah.
And
Inserting a new node, I think the list is straightforward, but placing one in front or in the middle of the list is harder. So I don't know what that would look like really, but
So, like, you know, on our problem where we eventually had walker.next would become null, right?
Yeah.
So instead of like basically you would transverse your linked list until you found that node where walker.next was null. And instead of saying walker.next equal to null, you would set it equal to the new thing that you want to add.
right.
So,
it would be at the end.
right, that would be at the end. If you're throwing it like in the middle or something like that, then you have to change a bunch of stuff. But
Change all of them.
well, you change all of its. It would depend if it's a singly list or doubly linked. If it's doubly linked, you have to change 3 total nodes, because you have to change the one before it, the one itself, and then the one after it. If it was only a singly linked, then you only change the one before it, and then you would have that point to what you're adding, right? And then the one that you're adding would point to what that one before used to point to.
Mm-hmm.
And that would be it.
Okay.
We can do that. Those would be good coding challenges. Like, because now that we've gone over linked lists, like there's a ton of those in LeetCode that I've just kind of been putting off because it's been like, well, we haven't really gone over linked lists very much, so but now we can do those if we want to.
Yeah.
For sure.
Kind of like some of the Big O stuff.
Mhm.
And then after tomorrow, I think, Jan, are you doing stacks and queues? I think that's right, isn't it?
Yes, tomorrow.
Okay, cool. So after tomorrow, we can do stacks and queues.
Nice.
Yeah. So that'll open up lots of stuff that we could use in LeetCode, at least. So
That's good.
I'm going to stop recording.